The next presentation will be by Oral5 Nie from Stanford about teaching an LLM to explore optimally. Please welcome Alan.
The mic is good? Okay, awesome. Hello, everyone. Thank you very much for helping me set up, and thank you for inviting me to give this talk. My name is Oral5 Nie. I'm a computer science PhD student at Stanford University. Today, I'm here to tell you a little bit about the topic of teaching LLMs to explore optimally, which is the work that I did with Google DeepMind with an amazing bunch of collaborators. And I'm giving a special shout out with my host, to my host, Yisu and Mimin Chen, who are kind of in the audience right now. This work has amazing contributions from Jonathan Lee, Bo Chang, Ed Shi, and Kwok Le as well. So to tell you a little bit about teaching LLMs to explore optimally, I want to first put your mind into this question, which is what is decision making? It's a very funny question because I feel like I spent the 5 years of my PhD trying to find an answer to this question, and I'm getting very, very close. So a lot of you guys already know what supervised learning is, which is kind of like finding a mapping between a set of input and output. But what actually is decision making? The answer that I was very close to finding for decision making is that decision making is really about understanding the known unknown. So what is a known unknown? In a classic decision-making setup, we often have a set of actions or a bunch of items. So we actually do know that these options exist out there. But what we actually don't know is how good these actions are or how good these items are. So imagine that you've never met someone, and then they ask you to recommend a movie, right? You're like, OK, so I made this slide in the middle of summer when Oppenheimer came out. So the example is about Oppenheimer. I guess now I would make it about Joker 2. So you're recommending Oppenheimer or Joker 2, and you're like, oh, OK. The person then tells you, I don't like them. Maybe I like Barbie instead. The sad part about this little interaction is that the only information you're able to get from this particular user is their preference for the action that you have already chosen. You don't know enough about all the other movies like out there. So decision making is really about, we know these movies are out there, but we really don't know whether the person that you're interacting with or the task that you're trying to solve would prefer them or not. So in the reinforcement learning community, in order to kind of solve decision-making, we actually need exploration. Because the best way for us to understand this kind of hidden information is to fully explore this known unknown. Usually exploration is explained under two different setups. One is for pure exploration, where we explore with some kind of fixed schedule. For example, in random exploration, we just try out each of the action randomly. Or for epsilon greedy, we try out a random action with epsilon kind of probability. However, the type of exploration I want to focus here is self-improving exploration. So what does this actually mean? This means that we're exploring with this very explicit purpose of trying to be able to solve the task as fast as possible and trying to earn as much reward as possible. A lot of algorithms have been proposed under this regime, which include UCB and Thompson sampling, posterior sampling RL, and bootstrap DQN. So we want to actually be able to see if LLMs have the ability to explore in context without the need to retrain, while interacting with the user, it's gradually trying to improve itself and trying to make the user more satisfied. So before we kind of pose this as a problem, we want to actually understand if the LLMs have the ability to explore at the moment, right? We've all seen amazing demos from GPT, from Gemini. Can they actually explore optimally? In order to study this, we want to kind of start with the classic setup, a problem that has been studied very rigorously in the machine learning community, which is the bandit problem. So the bandit problem is actually what is considered a one-step RL problem, where you have an environment. You can kind of like try out different actions or try out different items. Each of the item or action is associated with a distribution of reward, and each time you try out the action or suggest an item, you get a sample from that reward distribution. So by kind of interacting with the environment for about or however many rounds that you want to, you actually start to understand what the underlying reward distribution is, and your goal is to kind of find the best item. So after I was preparing this talk, some of my friends was like, oh, damn, why bandit? Why are we doing this? A lot of you guys might be a little bit unfamiliar with the bandit environment. And with this slide, I'm trying to kind of convince you that this actually is a perfect environment to study the LLM's exploration behavior. First of all, bandit problem is a reinforcement learning problem, except that it just has one step, and it doesn't have this explicit idea of state-dependent transition dynamics. So it's a much more simplified decision problem. But secondly, like it's a very popular problem model that's actively used in many of the companies. So for example, like Netflix, TikTok, YouTube, Spotify, they all like have some kind of bandit algorithm that's implemented, and it's giving you your next favorite TikTok video. So thirdly, this problem has been studied very rigorously by the theory community. And we already know like what kind of algorithm is somewhat optimal. We can see how these algorithms can help out LLMs. And finally, we might be able to do some cool analysis inspired by this type of like theory work in this problem setup. So I just want to quickly introduce you to one of these classic algorithms, the upper confidence bound algorithm. So the upper confidence bound algorithm explicitly calculates the exploration and exploitation value for each of the items here. So you can see it kind of like on your left side, there are 5 items there, and the confidence bound indicates like what's the estimated reward distribution for each of the item. We can run this algorithm on this bandit problem, and on the right, I'm showing the reward that's able to accumulate through these interactions. What's very interesting is that we can see that there is an exploration phase where it's not able to find like the best arm, but it's just like trying out different arms, kind of like not like reaching the top. But then later on, once it's able to identify the best arm or the best item to recommend, it just stays there. So it's kind of like matching the reward that we expect to see from that particular item. So to evaluate LLM on this kind of problem setup, obviously we can't just like dump the entire math model to it. So what we did is that we introduced Bandit Bench, which is a set of environments that's inspired by multi-arm bandit and contextual bandit with an explicit textual representation so that we can query LLMs and ask it what kind of action or decision it would make. For this particular setup, we're able to kind of like ablate or introduce many different configurations. So in the multi-arm bandit case, we're talking about kind of like clothes shopping or video recommendation. And for contextual bandit, we're thinking about kind of movie recommendation. By kind of like systematically ablating like how many items we want to recommend, or how different the reward distributions look like, we can kind of understand, we can evaluate LLM's ability to explore under these different settings. We can plot like its kind of like exploration curve, kind of like this, by seeing that it's accumulating reward as it's interacting with the environment, and it looks very similar. Like it has this very nice like curved behavior that we really want to see. So obviously, this is very nice in the sense that LLMs do have some capability of doing this. But because we introduce so many different environments, we have 16 different configurations for the multi-arm bandit. We want to summarize the behavior of these models by kind of by computing its pairwise win rate over these kind of domains. So we can see that for the UCB, it's able to kind of beat all the other LLM models in 16 out of 16 multi-arm bandit domains. So we can actually kind of take the average of that and compute like the overall win rate. So what this can actually tell us is that even though like LLMs have some initial capabilities to explore, there's still a very large gap between what we know is optimal. So I want to quickly tell you a bit about kind of like how can we make LLMs explore more optimally? Like what kind of strategies can we actually employ to teach LLMs to have this kind of like more optimal exploration behaviors? So we're going to kind of like introduce like 3 different kind of strategies. One is that we can think about introducing inference time support by kind of providing it with more information, or we can try to teach LLMs to learn from like Oracle experiences. So the inference time algorithm guided support, which we propose, is to just directly add these information from the UCB algorithm, which we treat it as an oracle. So we know that UCB explicitly calculate exploration bonus and exploitation values for each of the arm or each of the item. We can directly append them into the prompt itself. So how well does it do? So this is the performance from before without any kind of support. We can see that the gap between the best LLM Gemini 1.5 Pro and UCB is pretty large. By introducing this inference time support, by adding this information from the UCB, we're able to guide the LLMs to perform or to explore like much better than before. But that's not all. By kind of just like adding inference time support, like we're able to guide its behavior at inference time, but can we actually teach them in a slightly different way? We already know that LLMs are really good few-shot or even many-shot learners. Can we use few-shot full trajectory demonstrations to teach LLMs to explore better? We choose exploration trajectories from the Oracle UCB algorithm. Here, we really want to understand how well can we close the gap for LLMs under kind of the best situations. So we directly concatenate these demonstrations into the LLM context before it makes a decision. So kind of by using few-shot examples, we found something slightly a little bit perplexing, but I thought it's pretty interesting. So overall, it does actually increase the performance of the model. For example, for Gemini 1.5 Flash, in both the multi-arm bandit and contextual bandit domain, where it's able to increase its win rate. But for larger models like Gemini 1.5 Pro, somehow it's making it perform worse. So this is a little bit surprising, but not fully surprising, because it echoes the limitation of in-context kind of augmentation or changing prompt or prompt engineering in general. And it basically suggests that introducing more is not always better, since these exploration trajectories can get extremely long. So finally, we want to explore whether we can leverage supervised fine-tuning to distill exploration algorithms like UCB into weights. So this sounds extremely straightforward, but we still have a lot of design decisions to make. So earlier, I said we were trying to evaluate on 16 multi-arm bandit domains. So which domain do we really want to choose? Do domains actually make a difference? Is the domain of, let's say, recommending a movie, would it generalize well for recommending like a clothing item? So all of these are details that we explore kind of like in the paper, and please give it a read. To give like a very general high-level view of our result here is that by doing this kind of like fine-tuning on the full exploration trajectory, we're able to, first of all, get a much smaller model, which is Gemini 1.5 Flash, to surpass the performance of a very large model, which is Gemini 1.5 Pro. But also for contextual bandit under the specific setting, with just fine-tuning on about 40 different users, we're almost able to match the optimal algorithm's exploration capability, which is a UCB algorithm. I'm running a little bit out of time, so I'm going to skip this part, but you guys should definitely read the paper if you want to. So by using the bandit problem, we can actually analyze the exploration behavior in a very rigorous way. So without getting too much into the detail, usually the theory community will characterize the exploration behavior as 2 different types of regret growth. So either the linear regret growth or the sublinear regret growth. And the sublinear is actually what we want algorithms to behave. we can use the function form to kind of fit the empirical data of the regret of these models under the bandit setup. And then by fitting this particular function form, we can then interpret these two coefficients on these functions, alpha and beta, and then turn these like a billion different curves under different domains into a map with two coordinates of alpha and beta. And by kind of like putting all the models this way, we can very quickly see which models are very good at exploration and which are bad. The gold star is the optimal algorithm, which is the UCB algorithm, and all the other dots are different kinds of LLMs. And we can see that even though for the easy domain, some of the algorithms seem to be able to match the UCB's performance for exploration. On the harder domain, we're still pretty far away. And the last shout out is to the kind of the scaling law, where smaller models are much worse at exploring than larger models. So thank you guys very much for the opportunity, and please read the paper if you guys want to.
Thank you so much. We have time for one very quick question. No question? Okay, let's thank the speaker again. Thank you.